Now discuss about some abstract variation formulation. So many of the PDEs can be converted into that abstract formulation and get the existence uniqueness theory. So it will be very helpful. So we study abstract formulation. Abstract formulation. Okay. So let H be a Hilbert space, not necessarily H1 naught or H1. H be a Hilbert space and K a closed convex. So some functional analysis and weak topology, little more knowledge on weak topology is important to prove the result which I am telling. So it's better get to the closed convex set in H. And then what I am going to say, the theorem what essentially tells you, suppose you have a closed convex set here, it has to be a convex set. So closed convex set. So it is including the, so the best thing is the circle. Okay. And this is your K, and this is your whole thing is your H, and you have your point here, and what the abstract theorem tells you that there is a closest point and which can be characterized. That means any other point Z will be further than this one. Okay. So that is it. So that is what the theorem. This is a R2 you know it, this one, and you can see that if K is not closed, suppose you have not convex, suppose I have a set like this, and then I can have a point, I can have two minimum points. So you see. So that means if it is not convex, you may not get your uniqueness. So for example, if you have an annulus, this is not convex, this is your K, and then look at your point X here, then all the points on here are the minimal points, concentric circles. So you have infinitely many solutions, here you have two solutions. So there is no uniqueness, no uniqueness. These facts we are going to know uniqueness if K is not convex. Similar thing if K is not open, so let me write that one. So let us see a K is not open. So suppose K is not closed. So you have your X here, and then there is no minimum point here. This point is not in K. This point Y is not in K. So you see no existence. So even in the R2, but what it says that even in the Hilbert space the results are true, unique solution if K is a closed convex set. So that is the theorem I am going to state here. Theorem, okay, HK as above, HK as above, then for given X in H, there exists a unique Y in K such that instead of that you have to take the distance, distance is your norm here, norm of X minus Y is equal to minimum of norm of X minus Z. So you see for all Z in K. Okay. Keep. And then there is also a characterization, this we call it 1, and further y can be characterized by x so y in k x minus y z minus y is less than or equal to 0 for all z in k. You say, and this we call it a. That means if y is a solution of 1, then y is a solution of 2, and conversely if y is a solution of 2, it is also a solution of 1, and this is called the variational inequality. Variational inequality. Okay. So, you have your proof there. So, let me try to give a quick proof of that, verify the steps. So, any minimization problem, so proof. So, let me do it in. Okay. So, let d is equal to that minimum or infimum. I call it infimum because this is called infimum norm of x minus z in. How do you do? The moment you want to attack a minimization problem, you look for the minimizing sequence. This is the definition of the infimum. So, let Zn belongs to K such that norm of x minus Zn goes to D. So, what you want to prove? You basically want to show that Zn converges at least along a subsequence, and Zn converges to an element in that norm of x minus z, there exists an element y. Eventually you want to prove that Zn converges and that y is in K. So, that is what you are basically proving that. So, from here it is immediate that Zn is bounded in K, right. Zn is bounded, of course bounded in H or K, whatever it is, bounded in. That is trivial. From here you can immediately write norm of Zn because if Zn is unbounded, so I do not want to think. So, you verify this. If you are not understood something, it is better verify, because it is trivial, because if Zn goes to infinity, x is a fixed quantity, norm of x minus Zn will go to infinity. So, that is not true, D is a finite quantity. Now, this is a Hilbert space, this is where your functional analysis needed. So, you have to verify all these facts, or you have to understand your functional analysis properly along a subsequence. We do not make it a Znk etc., but along a subsequence we use the same thing, and I am sure these things are you are familiar already. Along a subsequence Zn converges to y. In H we do not know y is in K. Okay. So, there is another notion what are called weakly lower semi continuous. Weakly lower semi continuous. What is this lower semi continuity? So, we generally write it as weakly lower semi continuous. So, what is lower semi continuity? What is continuity of f? Continuity means if xn converges to x implies fxn converges to fx. That is the continuity of f. Lower semi continuity means there are motivations when, especially this lower semi continuity is an important concept in the minimization and optimization problems. Okay, because you are looking at the, so you need some sort of continuity, not full, you need some sort of an estimate from the lower side. So, lower semi continuity means xn converges to f, whatever be the topology implies your f of x less than or equal to lower limit of n tends to infinity of f x n. Okay. So, that is what your lower semi continuity. So, what is weak lower semi continuity? X n converges to x weakly. So, when you are defining some notions like weak, not that weak is always weak. So, weak lower semi continuity is not weaker than lower semi continuity. So, you have to see when you are giving a definition about weak, whether the assumption is weak or the conclusion is weak. Okay. If the assumption is weak and still you are concluding something, it is a stronger concept. So, just like that, with respect to the weak convergence, you want this to happen. So, this is a strong concept, n tends to infinity f of x. So, weak lower semi continuity implies continuity, lower semi continuity. Similarly, weakly closed means weakly closed implies closed. Closed means strongly closed, because for x n converges to x weakly, x n is in some k, then x is in k, you are demanding the assumptions are weak. Okay. With respect to assumptions, you are concluding the same thing. So, weakly closed implies closedness. The converse is not true. X n converges to a set is weak closed is not necessarily weakly closed, but then there is a result. So, a fact result, this is a part of the weak topology. Closed plus convexity. Convexity is an algebraic concept, it is not a topology. So, it retains, it is nothing to do with the topology. Closeness is a topological concept. So, this implies weakly closed. So, these are the things you probably need to know from the functional analysis. So, you have your weak lower semi continuity and you have your weak convergence. So, let me write down then along a subsequence, this is only Z n converges to Z weakly, I did not mention that. So, you are have, so these two things from here, it implies that all this whatever I discussed here on the right side of this thing implies y is in k, and you are and y is in k. One more remark further thing, and one more thing, the norm is weakly lower semi continuous. The norm is always weakly lower semi continuous. Yeah. So, these concepts you have to know. This implies y is in k and your norm of x minus y is less than or equal to norm of x minus lower limit of lower limit of, actually it is limit along a subsequence Z n, and that is nothing but your d, and d is in k. So, all this put together immediately gives you norm of x minus y is, because y is in k and that is smaller than t, because y is in k it has to be bigger because it is an infimum. So, these are the things you will prove. This is equal to the infimum norm of x minus z. Please, it is better that you go through the proof. Since now infimum is achieved, this is same as minimum, z is in k norm of x minus z. Okay. So, you have this one. So, this proves the existence. Now, what about the uniqueness? Okay. Uniqueness. So, you are using your functional analysis knowledge thoroughly now. So, by learning this course, your functional analysis will get improved. So, assume y prime is another solution, belongs to k is another solution You see, you can, it is better to draw picture. Okay. So, if you have two solutions, least solutions, okay, closest, you have to see that it will not happen. So, if this is y one solution, y prime another solution, now use the convexity. So, convexity means this whole line is inside any point here, that will use it more. So, this implies immediately y plus y prime by 2, half of that is in k for any t y plus 1 minus t for 0 less than or equal to t less than or equal to 1, which I will use it. So, half of y prime. So, with that you can prove that implies so d is the smallest one. So, d is less than or equal to norm of x minus y plus y prime by 2, because it is in that, it is an infimum. So, for any element d will be. So, for the analysis let me square it. So, here is a small exercise which you can show, you do some expansion etc., you can show that this is x minus y square, 2 is here, plus norm of x minus y square y prime square by 2. Compute that, you need to do some computation here, and minus norm of y minus y prime. So, this 2 is inside, okay, 2 square. Of course, this is equal to d square, this is x minus, this is d square by 2, this is d square by 2 d square by 2. So, that implies this is less than or equal to d square, because this is a negative term. That means that implies equality. That is implies d square, this is d square minus norm x minus y square, y minus y prime square, y minus y prime square is equal to d square, equality coming. So, this cancels, implies y equal to y prime. So, you prove the existence and uniqueness of the now you have to do the characterization. So, let me do that. So, you have you see, so you proved the existence and uniqueness dot. Now, you have to prove the equivalence of one word. Okay. So, let us prove the equivalence of 1 and 2, equivalence of 1 and 2, 1 and 2. Okay. So, assume 1, that is how you do it, right. Assume 1 and x belongs to H and y is in K, be the solution, be the solution. So, by convexity Tx plus 1 minus t. Now, you choose, you have to choose z is in K, arbitrary z. So, z tz 1 minus t y, but that is convexity is in K for all 0 less than or equal to t less than or equal to 1. Therefore, because y is the minimizing solution, so you have your x minus y is less than or equal to norm of x minus tz plus 1 minus t y, you see. Okay. So, what you do is that there is a small exercise which I will leave it, square expand, square and expand, cancel the terms, square and expand, cancel whatever it is, cancel, and then take t tends to 0 take t tends to 0, that will imply norm of x minus y less than or equal to norm of x minus z for, no sorry, that one, that is not what we want, that we know it. What we want, that will imply x, because once you score it and expand this one, square it and expand, you get an inner product term, that is nothing but, and then t tends to infinity, z minus y is less than or equal to 0 for all z in k, and of course your y is in k. So, this is your variation inequality, this is your 2. Now, conversely, assume 2, that means this is the one, and then again a very simple exercise, not need of an exercise. So, norm of x minus y square minus norm of x minus z square, you can calculate to be 2 into x minus y z minus y, that is minus norm of z minus y square. So, this is less than or equal to, this is 0, this is by 2, this is less than or equal to 0, this is a negative quantity, that implies norm of x minus y less than or equal to norm of x minus z for all z in k. That implies norm of x minus y is equal to minimum of norm of x minus z in k. So, you see this is your 1. So, you equivalent. So, you are minimizing problem which is a constrained minimization. A constrained minimization leads to inequalities, that is what you are trying to say. So, always constrain things, you may not end up with equations. If you have minimizing a constrained minimization lead to inequalities, but where there is no constraint, if the space are going to be a space subspace, then it will end up with equations. I will come to that if I get time today. So, we will do that, and then this y is called definition, y is called the projection of x, the projection of x in H onto K, you see. So, that means we denote that Pk. So, there is a mapping Pk from H to K given by Pk of x equal to y, where y is the solution to the minimization problem, where y satisfies 1 or 2, both are same, satisfies 1 or 2, solves the problem, minimization problem or variational inequality. This indeed is a projection in the sense of projection. You have learned it in functional analysis. You can see that Pk of x equal to, if x is in K, Pk of x equal to x, if x is in K, and repeating that way you can get Pk square is equal to Pk of x is equal to Pk. So, you see, you get it. Once you project it, it will be the same Pk square, because Pk of Pk is equal to Pk of x. Okay. This is always true, okay, because Pk of x is always in K. So, this is called a projection. There is an immediate corollary you can prove from the variational inequality. Pk reduces the distance between any 2 points. If x1, x2 belongs to H, then norm of Pk of the, it reduces the distance. Pk of x1 minus Pk of x2 is less than or equal to norm of x1 minus x2. Okay. The proof is obvious, easy, apply the inequality, you know for that one. By definition of pk of x1, x minus pk of x1, x1 minus pk of x1, z you just look at the inequality, z minus y, x minus y, z minus y is less than or equal to 0. So, you have your z minus pk of x1 is less than or equal to 0, x2 minus pk of x2, z minus pk of x2 less than or equal to 0. What you do is that here you take pk of x1 2, take pk of x2, z equal to pk of x2, you z is arbitrary. So, you can take this one, here you take z equal to pk of x1 and add the inequality and do things to derive this, this will and this will give this, okay, by subtracting and doing some process. One more remark, in the case of R2, geometrically that is a very nice thing. If you have a convex set and if you have an x here and if you have a projection here and this is your y and your z is here. So, and you have your x minus y, z minus y is less than or equal to 0. This essentially telling that this angle is obtuse. Okay. You cannot have an acute angle there. Okay. So, that is a kind of a geometric description about the projection. So, let me do a couple of things more, maybe a couple of things more. Yeah, so it is a definition and then maybe I will stop it since I do not have a time. So, we are interested in, we want to study, you see, we wish to study AUV equal to F AUV is equal to FE. I will denote FE means integral of FE. It can also be some other duality. I will make such remarks later for, you see, even for the L0 operator, and you want to find U is in H0. Keep that in mind. So, you have a definition, two definitions. We say A is elliptic, A is a bilinear form, okay, some H cross H. So, this is the case. With that in mind, H cross H2 are bilinear. Okay. A is called say A is continuous if there exists M. So, on the bilinear form I am defining thing for the which will coming from your ellipticity and boundedness of your differential equations. If there exists M such that modulus of AUV is less than or equal to M into norm U. Of course, every norm is in H, whatever be the norm you are defining. Okay. This is true for all UV in H. We say A is H elliptic if there exists alpha positive such that AUU is greater than or equal to alpha into norm U square for H. That is a lower bound U, and this should happen for all U in H. As I said, this is an example is, of course, we will see more examples which are the examples given by a thing, but if A is symmetric, suppose A is equal to Aij in that case. A is Aij, your Aij is n by n, then your AUV, where UV are in Rn. Okay. So, for UV in Rn, AUV you define to be V transpose AU, that is nothing but summation Aij Uj Ui, Aij Uj Vi is in this in Rn. Okay. So, indeed modulus of AUV is a matrix. Okay. N by n matrix. Okay. N by n matrix. Okay. AUV is less than or equal to norm A into norm. This vector is a modulus, is in Rn, modulus. Okay. AUV, and you can also, if A is symmetric, A is symmetric, positive definiteness. So, you see positive definite is a positive definite matrix, then you know that AUU is nothing but your U transpose AU, which is greater than or equal to some alpha into norm square, where alpha will be your least eigenvalue, least positive eigenvalue. You know that positive definiteness, the positive eigenvalue. So, with this I will stop here, and then I will make your abstract abstract inequality. Okay, I will do it in 2 steps when A is symmetric, and it is a straightforward representation theorem with little modification. But if A is not symmetric, it is one of the other interesting result. You can still prove the variational inequality, not as a minimization problem, but you can have the variational inequalities known as the Stambakia theorem. Okay, so with that we will continue in the next class. Thank you very much.